So in this lecture, I will explain the Propp-Wilson algorithm. So we have a Markov chain, which is defined on a space, on a finite space omega, and this Markov chain xn is irreducible, aperiodic, and has a stationary state denoted by pi. And what we want is to simulate pi, which means that we want to obtain a random variable whose distribution is equal to pi, or at least close to pi. So we have seen a way in which we can do that, and Propp-Wilson algorithm, it's an alternative way which has two advantages. The first advantage is that, in comparison to what we did so far, is that, well, we will have exactly a distribution, so we will produce a random variable whose distribution is exactly equal to pi. So remember, before we used to run the Markov chain for a very, very long time, and by using some estimate on the mixing time, claim that the distribution of xn is close to pi. Here, this algorithm has this big advantage, is that it will produce a random variable whose distribution is exactly equal to pi. And then there is also a second advantage, is that, well, it wasn't clear in our previous algorithm when to stop. So we need an estimate on the mixing time to know how large we need to take n, so how large we need to run this Markov chain in order to get something which is approximately equal to pi. Here, we know exactly where to stop. So the Propp-Wilson algorithm provides you, an algorithm, a rule, to tell you when to stop your Markov chain. So these are the two advantages. The drawback you'll see is that first we will have to run a very large number of Markov chains. Actually, for each point or configuration in omega, we need to run a different Markov chain. And there is also a peculiarity in this algorithm, is that we run it in negative times, while usually one would think that you should run Markov chain in positive times. Well, in this one, we will run it in negative times. So let me fix the notation. So we have this state space, omega. Omega has, let's say, the elements will be represented by eta 1, eta 2, up to eta m. So the total number of elements of omega is equal to m. And we have a sequence u1, u2, and so on. So this is a sequence of id random variables which are distributed uniformly on the interval 0, 1. And we have also functions phi for each. So these functions phi are defined from omega to 0, 1 to omega. And these functions tell us how to use these random variables in order to simulate a chain xn. So remember, these functions are so that if I define xn plus 1 as phi of xn un, then this process xn, it's a Markov chain which has some fixed transition probability. So let me represent by P the transition matrix of the chain I'm interested in. So these phi, and we have seen how to do it, these phi are defined in such a way that xn plus, that this formula defines a Markov chain which has transition matrix given by P, where P is our chain, so the transition matrix of the chain whose invariant measure is pi. So remember, we want to, so the problem, let me summarize the problem again. We have a space omega, we have a probability measure defined on omega, and we want to create a random variable whose distribution is close to pi. So we want to, here actually, we will define a random variable whose distribution is exactly equal to pi. And how we do that? Well, we define a Markov chain, which is characterized by its transition matrix P. And by these functions and these random variables, we can simulate this Markov chain. And now I will explain what is Propp and Wilson idea, how to use this Markov chain in order to find a random variable whose distribution is exactly equal to pi. So let me explain you the algorithm. We will fix a sequence n1, n2, which is increasing. So np is strictly smaller than np plus 1. So typically, I will take the sequence 1, 2, 4, 8, and so on. So this will be my sequence. During this lecture, I could have fixed any other sequence, but this one is fixed. Now, you set, so this algorithm is done in stages. So assume that you're at stage 1. So stage 1 means that you do the following. Well, you start running a Markov chain, and this Markov chain will be represented by xt. So P, because we are on stage 1, P will represent the stage, and K will be representing the initial state of that chain. So remember, we enumerate the elements of omega. So omega is n1, n2, up to eta m. And so K runs, so P is larger than 1, and K runs from 1 up to m. And this Markov chain will run from minus n1 until 0. Mind here n1, actually this is np, but at stage 1, p is equal to 1. So this chain will be defined from in the negative interval of time from minus n1 up to 0. And how do we define these sequence? Well, as I said, you start this sequence at time minus np, setting it to be equal to eta k. So at time minus np, this chain starts from eta k. So the chain k starts from eta k. And this you do for all k. And now you define the chain by using the function phi. So this chain pi k at time t plus 1, so mind t here it's negative, will be equal to phi of x p k at time t. And here I'm using u, but u, it's my sequence u1, u2. This is the sequence of, this is the IID sequence of uniform random variables. So I'm using here u at minus t. So t, as I said, it's running from, and this is t going from minus np, less or equal than t, less or equal than minus 1. Right, so for t in this range, you start at minus np, so you define it in this way. Then at minus np plus 1, you use the value at minus np, which is eta k, and you use u of minus np, which is u np. You use this random variable in order to define the state at t plus 1. Mind that you are using the same u for all chains. So this u does not depend on k, it's the same for all chains. And so you run, by using this formula, this chain. So mind that this is a chain. So this is a Markov chain whose transition matrix is P, and it runs for minus np up to, if you take t equal to -1, here you get that this is 0. So you get a value at time 0 for that chain. Mind here that since t is running from -np to -1, you minus t, it's running from 1 up to np. And what's very important here is that you're using the same random variable u minus t to update all Markov chains. So mind that you are running at the same time m different Markov chains. So you run these Markov chains, and at time 0, you get values. And, well, two things may happen. Well, maybe all these chains take the same value. So maybe x p k at time 0, it's equal to x p j at time 0, and this for all j and k in 1m. So if after running your chain from time -np up to time 0, you find that at time 0, all the chains have the same value, you say that you reached an end, so this algorithm reached an end, and you set y to be one of these values. So x, p, k, 0. So you set y to be one of these values. Well, if not, so let's say that this is step 1, so this is step 2, so this is step 3. If this happens, you're happy, and you define y to be that. But maybe not all values are equal. So maybe there exist, if not means that there exists a j different from k, such that x p k 0 it's equal different from x p j 0. So maybe there are two initial states when you run this Markov chain at time 0, you don't get the same value. So in that case, what you do, well, you increase p by 1. So you change p from p to p plus 1. So which means that if you start with p equal to 2, you go to p equal to 1, you go to p equal to 2. And then, so you change the value of p, and then you repeat step 2. You go back to step 2, but now the value of p has changed. So you started with p equal to 1. You run that chain. At time 0, you obtain two different configurations which give you different values. So what you do is that you change p to 1 to 2, and you repeat this procedure now by using p equal to 2. So instead of starting at minus n1, now you started at minus n2. So instead of starting at -1, now you start at -2 or -4, -8, and you define a new chains, a family of Markov chains in the same way. But mind that at step 1, we used in this definition the random variable, well, minus t running from -np to 1 means that t minus t here was running from 1 to np. So in step 1, we use the variables u1 up to un1. Now in step 2, you will use the same random variables together with the ones going from eta u n1 plus 1 up to u n2. So what I want to stress here is that these random variables which were used to define the chain x1k are now used to define the chain x2k. You don't throw them away and use new random variables. You keep them and you use them in the definition of the second family. And you proceed as before. So you run these chains from minus n2 up to 0. Then at time 0 you check if all values are the same. If all values are the same, you are happy. You define your random variable y as one of these values. Otherwise, you repeat the iteration. So you move p from p to p plus 1, and you go back to step 2. And you do that until you reach one situation in which all these values agree, and you define y to be this value. So this algorithm, if it ends, provides you a random variable, which I'm representing by y, which takes value in omega. So y, it's one configuration, and it's the result of this algorithm. So it might not end. I'm not claiming that it always ends. What I'm claiming is that, well, if it ends, it provides you a random variable, it provides the value of a random variable, which takes value in omega. It provides you a random variable y. And what I claim, and what we'll prove after I give you an example, is that this random variable y has exactly the distribution pi. So what I claim, what I will prove in a second, is that the distribution of y is equal to pi. So which means that if the algorithm ends, then the random variable y produced has a distribution exactly equal to pi. So now I will present, just to fix, to make sure that you understood what is the algorithm, I'll give you an example, and after the example I will prove a theorem which claims that the distribution of y is given by pi. So here is an example. I'm taking omega with 4 configurations, eta 1 up to eta 4, and my sequence n1, n2, n3 will be the sequence I propose, so 1, 2, 4. So we started at stage 1 with p equal to 1. So here is time 0. We start the 4 chains at time minus 1, one which starts at eta 1, one at eta 2, the other at eta 3, and eta 4. And this is the result. So eta 1 jumped to eta 1, eta 2 to eta 1 by running our algorithm. So I'm taking here p equal to 1. I'm taking the random variable u minus t here. So I'm first at stage 1. So for p equal to 1, t, it's running from 0 to minus 1, as it's drawn here. And so I'm using actually here only the random variable u1. So by plugging u1 in this formula and by replacing x minus 1, 1 k by eta k, I get the value of x at time 0, and this is what this computation produced. So starting from eta 1, I reached at time 0 the configuration eta 1. Starting from eta 2, I reached eta 1. From eta 3, I reached eta 4. And from eta 4, I reached eta 3. So this is the result of this equation with u1 being used. And as you see here at time 0, not all configurations are equal. If I start from eta 4, I reach a configuration which is different from the one I reach at time 0 if I start from eta 1. So my algorithm tells me that, well, I have now to change p equal to 1 from p equal to 2. So now my chain will run from minus 2 up to time 0, which means that I will use now the random variables u1 and u2 to define these new chains. But mind, I'm using the same random variable u1 to go from time 1 to time 0. So if I take here t equal to minus 1 in this equation, I'm using the same variable for p equal to 1 and for p equal to 2. Which means that if for the chain 1k, I jumped from a configuration xi to a configuration xi prime, so which means that if for the chain 1k at time -1, the process was at xi and it jumped to xi prime at time 0, the same will happen to the chain x2k. So if a chain x2j is such that at time -1, it takes the same value as the chain x1k at time -1. So if these two values coincide, this means that at time 0, I will jump to xi prime, because I'm using here exactly the same variable. So let me repeat. For each stage, p equal to 1, p equal to 2, p equal to 3, I'm defining different chains. But these chains have something in common which is very important, which is observed here. And this is, assume that I'm running a chain at stage p, which starts from k. And let's say that p, it's smaller than q. And let's assume that, well, at time -1, this chain coincides with the chain defined on stage q, which starts at j, but at time -1, these two chains coincide. Well, this implies that this chain pk at time 0 takes exactly the same value of the chain qj at time 0, because I'm using the same random variable. Because to compute this value for this chain, I will just, so I want here t is -1, so this is 0. So I want the value at time 0 of the chain pk. So I'll plug that. But at time -1, this object coincides with xqjt. And for both of these chains, I'm using the same random variable. So since xpk it's at -1, it's equal to xqj at -1, the first coordinate will coincide. Since the second coordinate coincides also, I get that this identity holds also at time t plus 1, which is 0. And therefore, I can generalize that, saying that if these two chains coincide at some s, then they will coincide at t for all t larger or equal to s. And this is very important. This is a very important property of this algorithm. And this is illustrated here by the colors red. Because from the first step, I know that from time -1 to time 0, if I'm at eta 1, I jump to eta 0. If I'm at eta 2, I jump to eta 1. If I'm at eta 3, I jump to eta 4. If I am at eta 4, I jump to eta 3. And these are exactly what the red arrows show. So I just repeated the arrows, and the new information, it's coming from this new column, which tells me that from time -2 to time -1, I jump according to these rules. These were obtained by plugging u2 in this equation to get the values of x, now stage 2, so x2 at time -1 for all values of k. And, well, so this means that now, if I start from this 4 configuration, you see that if I start here, I will reach eta 1. If I start at eta 3, I also reach eta 1. But if I start at eta 2, I'll reach eta 4. And if I start, so all these 3 chains attain the same configuration at time 0, but this configuration, this chain, which starts at eta 2, will reach at time 0 the configuration eta 4. So the algorithm still did not end, and we have to go from p equal to 2 to p equal to 3. Mind that if I can show that at time, starting from now, we will start from time minus 4. So that if I start at time minus 4 and at time minus 2, I reach only these 3 configurations, then I'm sure that at time 0, I reach the configuration eta 1. But the important observation here is that the update will use, again, U1 and U2. And therefore, these arrows are exactly the same as the first arrows. And now I use eta 3 and U3 and U4 in order to compute the jumps of these chains from time minus 4 to minus 3 and from times minus 3 to minus 2. And now what, well, we follow these arrows. So if you start from at time minus 4 from configuration eta 1, what you do is you reach eta 1. If you start from eta 2, you reach eta 1. If you start from eta 3, you reach eta 1. And if you start from eta 4, you also reach eta 1. So what you get is that at stage 3, the algorithm ended and produced one value. So this algorithm produced for these values of u. So you see that all the randomness, it's coming from these random variables u. For these values of the random variable u, it produced the random variable y, which is equal to eta 1. And of course, if I change the values of u, I will get a new set of arrows which will produce a different outcome. So this is a random variable which takes values on omega, and this is the outcome of Propp-Wilson algorithm in this very simple case. So, but what you need to keep in mind is that this property, that we are keeping the same use as we go backward in time, and therefore a piece of the history is known when you go from one step to the other. We are just adding a new set of randomness, adding a new information to this, but we are not changing entirely the distribution of these arrows, so the jumps of our process x defined by this equation. So this is Propp-Wilson algorithm, an example to illustrate this algorithm. I hope that now you understood it, and what I will do is I will prove that if it ends, y has a distribution, so the distribution of y, it's given by the invariant measure of the process of the Markov chain x. So this is the next step. Before I proceed, I forgot to say something which is very important, is that, well, if now I run this Markov chain at stage 3, now I could go and define a new, go to stage 4. And what I claim is that at stage 4 or 5 or 6, the outcome will be the same, because in stage 4, I would just add here 4 more times. So I'll start later in time, I will run my chain, but whatever the outcome at time minus 4, I know that at from time minus 4 to time 0, all the chains will get the same value. So the final value, the value at time 0, does not depend on the history of the chain before time minus 4. The value at time 0 of this chain, it's fixed by starting at time minus 4 from all configuration, I reach a unique configuration time 0. It means that whatever the past history of this chain, whatever this chain does before time minus 4, given that this is what it will do between time -4 and time 0. Whatever the past history, all chains will end at eta 1. And so I could have not stopped at stage 3 and went to stage 4, but the outcome of this algorithm will be the same at stage 4, 5, 6, and so on. So the outcome of the algorithm is once it ends at the same value at all stages. So here is a theorem. So let's say that we have a Markov chain, which is aperiodic and irreducible. So now let's assume that the Propp-Wilson algorithm ends with probability 1. So let's assume that, well, if we run this algorithm, we can show that it will end. Let's represent by y the outcome. So y, it's, well, the value that the Propp-Wilson algorithm provides. So what I claim is that then the probability that y is equal to a configuration eta k is exactly equal to pi of eta k, where pi is the unique stationary measure for the Markov chain. So this is, and as I said, well, this algorithm has two very nice features. The first one is that you know exactly when to stop, because you have a rule which tells you when to stop. If all the values of all chains are the same, you stop, otherwise you continue. And the second very interesting feature of this algorithm is that it gives you precisely the distribution pi. So the probability that the outcome is equal to eta k, it's equal to pi of eta k for all k. So this is also a very nice feature of this algorithm. So let's prove that. So let me call the t the time at which the stage, so t is the stage at which the algorithm ends. So to be precise, what do I mean? I mean that, well, you know that I represented by p the stage, so we start from 1, 2, and so on. So this means that t equal to p, or less or equal than p. So the stage, the algorithm ends before stage p. This means that if I run the process at stage p, starting from k at time 0, so this is equal to x p j 0 for all k and j. So, meaning that the algorithm ended before or at time at stage p means that if I run the algorithm at stage p for any two different configurations, the result I get at time 0 is the same. So, saying that the algorithm ends with probability 1 means that the probability that t it's less than infinity, it's equal to 1. So this is the hypothesis. Fine. And now what I will do is I will, for each p, I'll construct a new chain. And this chain, which will be represented by x tilde p, it's a Markov chain, which runs from minus np up to time 0. And, well, how it defines? at time minus p the initial value of this chain will be the stationary measure, will be given by the stationary measure. This means that the probability that x tilde p minus np it's equal to xi, this is exactly given by pi xi. So before I had, remember, these chains pk or pj, t. Well, these chains were defined in such a way that at time minus np, I started from the configuration eta j. Now, well, this one it's slightly different because, well, it doesn't start from one specific configuration, but it starts from a configuration xi with a certain probability. And once this configuration xi has been determined, I just follow the, I just define this chain by using the same update as I used for x. So this means that the chain x tilde p at time t plus 1 will be given by my function phi of x tilde p at time t u minus t. So I'm using exactly the same update for this chain and for the chains x pj. So the same update is used. And what's clear is that since I'm starting from pi, and since this identity provides me a Markov chain with transition probability p, this means that since pi is stationary, this means that at time 0, the distribution of this chain is equal to pi. So the probability that x tilde p at time 0 is equal to xi, then this is also equal to pi of xi. Because by using this equation, this defines a Markov chain with transition matrix P, and pi is the stationary state of this Markov chain. Therefore, if at time minus np the distribution is pi, at time 0 the distribution it's also pi. So this is what I know. Now, let me fix an epsilon positive. Since this probability is equal to 1, this means that I can find a p finite such that the probability that t is less than pi, it's larger than 1 minus epsilon. I could also write that the probability that t is larger than p, it's bounded by epsilon, which is the same thing. Since, well, this is the probability that it's finite is equal to 1, this means that as I let p increasing to plus infinity, this probability is 1, and therefore I can find a p sufficiently large for that to be bounded below by 1 minus epsilon. Now, I want to estimate the difference. So let's recall that y it's the outcome of the Propp-Wilson algorithm, and I want to estimate what is the difference between the probability that y is equal to xi and the pi of xi. I want to show that this is small. Actually, I want to prove that this is smaller than epsilon. Fine, but this is equal to pi, y equal to xi, so let me write it in this way, minus, and here, well, since pi xi it's equal to this value, this is equal to minus x tilde p of 0 equal to xi. Now, I can rewrite this difference as the probability that y is equal to xi and x tilde p0 is equal to xi. So I'm decomposing this event according to this event or its complement. And the probability that y is equal to xi and x tilde 0 p it's different from xi. And I will do the same thing for the second probability. So this second probability is equal to minus the probability that, so I have a minus here, x tilde p0 it's equal to xi and y it's equal to xi minus the probability that x tilde pi it's equal to xi and y it's different from xi. So now of course, this expression cancels with that one, and so this difference it's equal to this expression minus this expression. So up to now, I proved that this difference it's equal. So let me write it. It's equal to the probability that y is equal to xi, that x tilde p0 is different from xi, minus the probability of the complement, which is y it's different from xi, and x tilde p0 it's equal to xi. So now I'll get an upper bound and lower bound. So let me show the lower bound. The upper bound it's proved exactly in the same way. So for the upper bound, well, this is positive, so this is negative. So this probability it's bounded by that one. And this probability here, it's bounded by the probability that y it's different from x tilde p of 0. That's clear. If y is equal to xi and x tilde p0 is different from xi, this means that y is different from xi. And well, this event, if the output of the Propp-Wilson algorithm, which is y, which are represented by y, it's different from this one, this means that at stage p, the Propp-Wilson algorithm didn't end. So what I claim is that this is probability that t it's larger than p. Because if t it's smaller than p, so let me show that actually this event, t is smaller than p, it's contained in this event, y equal to the complement of this event, which means that y is equal to that. Because if t is equal to p, what does it mean? It means that whatever at stage p, whatever the initial configuration I choose at time minus np, when I reach time 0, all these configurations are equal. All these configuration x p eta 1, now I'm representing by eta 1, what before I represented by 1. So if t is less than p, which means that the Propp-Wilson algorithm ended before stage p, we have seen that this means that if I run the process, so if I run Propp-Wilson algorithm at stage p, I also end at the same configuration at time 0, which means that x0 p1 it's equal to x0 pj for all j, all possible j. So all j between 1 and m where m represents the total number of elements of omega. And in particular, this means that x tilde p0, it's also equal to one of these configurations, because I started at a random position, but at time minus np. But whatever the random position I chose, when I reach time 0, I get, well, one of these positions, but they are all equal. And therefore, y, which is this random position, it has to be equal to the position of the chain I just defined, right? Because I'm using here the same updates, which means that whatever the initial position at time minus np, when I reach time 0, they are all equal. In particular, also x tilde should be equal to these positions, because in x tilde, I started from a random position, but whatever random position I choose, at time 0, I end up at the same position, which means that y has to be equal to x tilde p0 if t is bounded by p. If t is less or equal than p, then y is equal to that configuration, which means that this set is contained in that one, which means that the complement, this set, is contained in this one. And we have seen that this one has probability bounded by epsilon. So this proves that this probability, this difference, it's bounded by epsilon, and we can also obtain a lower bound by saying that, well, this is positive, and so this is bounded by minus the same quantity, because this quantity, it's also, this quantity is bounded by that one, so this difference here, it's bounded by this probability, and this probability is bounded below by minus epsilon. So we proved that this expression is between minus epsilon and epsilon, which proves that its absolute value, it's bounded by epsilon. Since we are free to choose epsilon, by letting epsilon to 0, we conclude that indeed the distribution of y is even by pi, and if the algorithm, Propp-Wilson algorithm, ends at in a finite time. So this proves the theorem, and now I want to discuss some questions about the Propp-Wilson algorithm. So when studying this Propp-Wilson algorithm, you might have an objection. First is that, well, you have to run m chains. So remember that omega is a space eta 1 up to eta m. M represents the total number of configurations. And typically, you would maybe in the coloring model or in the hard-code model, if you are working in a two-dimensional space, which say have L sides, L by L sides, the number of configuration will be of the order of 2L squared. So if L is equal to 10, that will be 2 to the order 100. And this is, of course, too large. You don't want to run 2 to the power 100 Markov chains. So this is a first objection. And we will see that in certain cases, we don't need to run them all. But if there is an order in the space, we can, we can reduce the number of chains to 2. But before I discuss that, let me discuss some temptations. So the first usual temptation is to run the Markov chain forward in time. And so instead of running it from time minus np up to time 0, you may ask, well, why don't we run the chain from time 0 up to the first time in which all agree? So one proposal, alternative algorithm to the Propp-Wilson might be the following. Well, let's say that I still have my space, omega, with m points. So let's run m different Markov chains, each one at time 0 starting from eta k. Let's use the same sequence of uniformly distributed random variable to to run the chain. So let's define x t plus 1 k to be phi x t k u t. And let's define t to be the first time, so the infimum of all time t, such that all these chains agree. So x k t is equal to x j t for all k and j. And let me call the product y. So the output of this algorithm, let me call it y. And y would be therefore the value of one of these chains at time capital T. So, well, this seems a reasonable alternative algorithm, because instead of running it backward in time, you run it forward in time. The first time they all reach an agreement, you are happy, and you define this as the outcome of your algorithm. So let's say that this is wrong with an example. So let me provide you an example in which we can compute y and show that y is not it's not distributed according to the invariant measure. So this is a very simple example. It has only two states, 1 and 2. And if you are at 1, you do the following. You jump with probability 1/2 to 1, and with probability 1/2, you jump to 2. While if you are at 2, you jump to 1 with probability 1. So this chain, it's clearly aperiodic, because you jump from 1 to 1 with a positive probability, and it's irreducible, because you can jump from 1 to 2 and from 2 to 1. So this chain, it's aperiodic. It's irreducible. It has a unique invariant measure pi, and you can compute. I leave it to you to check that pi is given by pi of 1, it's equal to 2/3, and pi of 2, it's equal to 1/3. This is a very simple computation. Now, let's assume that you run. So you started from 1 and 2, and you run your Markov chain by using these this algorithm and this IID sequence of uniform random variables. So let's see, t is the first time they meet. So at this time, the process met. This means that at time t minus 1, they didn't meet. So which means that one of the process is at 2, and the other process is at 1. So one of them it's at 1, and the other it's at 2. And we know that at time t they meet. If at time t they meet, this means that, well, 2 jumped to 1 and 1 stayed at 1. Because if 1 jumped at 2, since the probability that you jump from 2 to 1 is 1, this means that the one which was at 2 necessarily jumped to 1. And since they met, this means that the one which was at 1 also jumped to 1. And therefore, this means that when they meet, both processes are at configuration 1, which means that the probability that y it's equal to 1, y it's the output, so this is the probability that xt it's equal to 1, well, this is 1. Because when they meet, they always meet at the configuration 1. And of course, 1 is not the probability of the configuration 1 of 0.1. Probability under the stationary state of 1 is 2/3, while this algorithm is giving us that an output always equal to 1. So this example tells you that, indeed, this first temptation, which is to run the process forward in time and couple them until they meet. so couple them by using the same IID random variables u. That does not work because in this example the distributions do not coincide. So that's the first temptation, and this is an example to show, to convince you that, well, it doesn't work, it's wrong. The second temptation, it's the problem of keeping the same values, the same random variables for different stages. So why bother to keep the values of these random variables u1, u2 at each stage? Maybe you have a long sequence of random variables, so you need to store these. That's time-consuming, computer-consuming, so maybe you want at each step to generate a new family of random variables in order to run the Propp-Wilson algorithm. So the second temptation is to run a new sequence of random variables u. So let's say that at stage 1 you use the random variable u1, 1, 1, 1, 2, and so on. At stage 2 you use the random variables u2, 1, u2, 2, and so on, and so on. So renew these random variables when running the Propp-Wilson algorithm. And let me convince you that this does not work either. So let me take the same example, 1, 2. So remember, 1 you're jumping with probability 1/2 to 1 and 1/2 to 2, while in 2 you jump with probability 1 to 1. And in station state it gives weight 2/3 to 1 and gives weight 1/3 to 2. Now, okay, let me compute what is the probability that y is equal to 1. So y is the output of this new algorithm in which at each stage I use a different set of random variables. Let me call t. So t is the stage at which I end. So this is the ending time. So remember that t is equal to p if x, well, in our case, we have only 2 random variables, which means that if x p1, 0, it's equal to x p2, 0, and if x q1, 0 is different from x q2, 0 for all q between 1 and p. So t equal to p means that the algorithm was successful at stage p and wasn't successful at stage q for q less than p. And well, I will write this probability according to the possible values of p, of t. So this is equal to p larger than 1, the probability that y is equal to 1, t equal to 1, to p. And, well, and this is clearly larger or equal than the probability for p going from 1 to 2 of this probability. So let's compute this probability for p equal to 1 and then for p equal to 2. For p equal to 1, so here we are at time 0. We started at time -1 from the configuration 1 and the configuration 2. We want the algorithm to be successful at time, so 2 jumps to 1. And we want the algorithm to be successful at stage 1. This means that the value, they have to coincide, the value at 0 has to coincide. So this means that we want the process starting at 1 to jump also to 1. And what is, well, this probability, you see that 2 will jump always to 1, but 1 jumps to 1 with probability 1/2 and jumps to 2, so this probability happens with probability 2. So the probability that you end at stage 1, it's 1/2, and if you end at stage 1, the output, it's indeed 1. So this probability here, with p equal to 1, it's equal to 1/2. Correct? So this is the probability that t it's equal to 1 and y it's equal to 1. With probability 1/2, 1 jump to 1 and 2 jump to 1. So they met at time 0 and they are at 1. So now what I have to compute is this probability when t is equal to 2. So I want the probability that y it's equal to 1, t equal to 2. And I will compute this probability as the probability of y1 equal to 1, given that t it's equal to 2, times the probability that t is equal to 2. And we will compute separately these two probabilities. So let me first compute the probability that t is equal to 2. Well, if t is equal to 2, what does that mean? It means that the stage 1 of the process did not provide an output, but the second stage provided an output. The probability that the first stage provides an output is 1/2, so the probability that it does not provide an output, it's 1/2. So this 1/2 comes from the fact that the probability that stage 1 did not provide an output. Now, this probability is independent from the probability that the second stage provides an output, because in the second stage, we use a second family of independent random variables to construct the chain. So producing or not producing an output in the second stage, it's an event which is independent from producing or not producing an output in the first stage. So this is why this probability, which corresponds, we did not produce an output at stage 1 and we produce an output at stage 2, it's actually a product of probability. The first one accounts for not producing an output at stage 1, and now we have to compute the probability that we produce an output in stage 2. Well, so let me compute this probability here. So this probability, now we are at stage 2. So here is time 0 times -1 times -2, and we are running this chain. Well, this, let's say, it's configuration 1, this is configuration 2, and I know that I always jump from 2 to 1. So these arrows are always present. But on the other hand, from stage 1, from state 1, we can jump to state 1 with probability 1/2, or to state 1 with state 2 with probability 1/2. This means that here I can draw with probability 1/2 an arrow from 1 to 2 and 1 to 2, an arrow from 1 to 1, sorry, and an arrow from 1 to 2 with probability 1/2. So since there are 2 steps, I have 4 possibilities. So let me draw them all. So this is one possibility. This is a second possibility. And this is the third possibility. So you see that each of these possibilities has probability 1/4, because each of these arrows has a probability 1/2. So you see that in this case, we produced an outcome which is 1. In this case, we produced an outcome which is 2. In this third case, we produced an outcome which is 1, and in this fourth case, we produced no outcome. So out of the 4 possibilities, each one having probability 1/4, 3 of them produces an output. So the probability that starting running from time -2 to 0 produce an output is 3/4. So the probability that the algorithm ends at time 2, it's 1/2 times 3/4, which is equal to 3/8. And so let me insist that this 1/2 comes from the fact, from the probability that no output was produced at stage 1, and 3/4, the probability that an output is produced at stage 2. So the probability that t is equal to 1, it's equal to the product of this probability, which is 3/8. So this is the probability that t is equal to 2. Now I have to compute what is the probability that the output is 1, given that t is equal to 2. So that t is equal to 2, I know that this event did not occur, because in this event there is no output, and therefore there is no output, and therefore it's excluded, this event it's excluded by the fact that I'm conditioning on the event that the output is produced at stage 2. And since the output is produced at stage 2, I don't care what happened at stage 1. In order to know the output, y, I just need to observe the second stage. And by observing the second stage, I see that there are 2 possible outputs, either 1 or 2. Each of these events has the same probability, 1/4, which means that the probability that the output is 1, it's equal to 2/3. There are 3 possible outcomes, each one has the same probability. In 2 of them, the output is 1, therefore the probability that y is equal to 1, given that t is equal to 2, that this is 2/3. And therefore, this gives me that the probability that y equal to 1 and t is equal to 2, it's equal to 2/3 times 3/8, and that makes 1/4. So we computed this second probability. The first one was y equal to 1 and equal to 1 was 1/2. So that gives me another 1/4. So the sum is equal to 3/4. And, well, 3/4, it's strictly larger than 2/3, which is pi of 1. So we see from this computation that by using a different family of, an independent family of random variables at each stage, produce an output whose distribution is not given by the station state. This example shows that this alternative algorithm is bad because it produces an output whose distribution is not the invariant measure. Therefore, you might be tempted to renew these, to take at each stage an independent set of random variable. The problem is that this will give you a wrong answer. So these 2 examples illustrates the interest of the Propp-Wilson, because it gives you the correct answer in a quite simple algorithm. Of course, the backdraw, as I mentioned already, is that you need to run a large number of Markov chains in order to produce this output. But we will see that in some examples in which you have an order, so if your set omega, it's an ordered set, and if it has a maximal and a minimal element, then instead of running this bunch of Markov chain, we can run, well, and if the dynamics preserve this order, in a sense I will explain maybe in this lecture or maybe in the next one. So if the order is preserved by the Markov chain, then we can run, instead of running m different Markov chains, we can run just 2 Markov chains and it will produce the same outcome. So given our set omega, I'll say that this symbol it's an order if the following relations holds. First, I'll ask eta to be less or equal than eta for all configurations eta in omega. Then I will require that if eta it's less than xi, and if xi it's less than eta, then eta is equal to xi. And finally, I will require that if eta it's less than xi, and if xi it's less than zeta, then eta it's less than zeta. So these are the relations required to be an inequality or an order in a set. So I'll say that omega it's an ordered set if there exists a relation which satisfies these 3 conditions. Mind that I'm not requiring that if I take two configuration eta xi, there is one which is less or equal than the other. So I'll say that this order, it's a total order if this last property holds. So this order, it's a total order if besides these 3 properties, we have the 4th one, which tells us that for all eta xi in omega, I have either that eta it's less or equal than xi, or xi it's less or equal than eta. So the set it's totally ordered if this 4th condition holds. So let me give you 2 examples. So first, omega will be equal to 1, 2, up to m. And this is clearly a totally ordered set. But a more interesting example will be omega to be the set 0, 1 to some power v. So these configurations are represented by eta. So for x in v, eta x might be either equal to 0 or equal to 1. And so I will define an order in this set. I will say that eta it's less or equal than xi if eta x it's less or equal than xi x for all x in v. So this relation, of course, satisfies all these 3 conditions. Of course, eta it's less or equal than eta because eta x is less or equal than eta x for all x. Now, if you take 2 configurations such that eta it's less than xi and xi is less than eta, this means that eta x it's less than xi x for all x, and xi x it's less or equal than eta x for all x. So by the totally order of the real numbers, this means that eta x is equal to x for all x, which means that eta is equal to x, to xi. So this means that the second condition is also satisfied. And this one it's also clear if eta x it's less than xi x for all x, xi x less than zeta x for all x. This means that eta x is less or equal than zeta x. So this order, this is an order in this set, but it's not a order. It's not a total order. Say that you have 4 points, so that V, this set V consists of 4 points. And let me draw you 2 configurations. So this is configuration xi, this is configuration eta. So let's say that eta it's 1 at this site and 0 elsewhere. Xi it's 1 at this site and 0 elsewhere. And it's clear that eta is not less or equal than xi, and xi is not less or equal than eta. So the order I just defined, it's not a total order. So that's very nice. We have a total order. And now, final definition that I will use, I will say that eta in omega, it's a minimal configuration if eta it's less or equal than xi for all xi in omega. And I will say that eta prime, it's a maximal configuration if xi it's less or equal than eta prime for all xi in omega. And in our example, 0, 1 to the power v, of course, the configuration eta such that eta x is equal to 1 for all x. It's a maximal configuration. So maybe I should call that prime. So eta prime x equal to 1 for all x, it's a maximal configuration. And the configuration eta x is equal to 0 for all x is a minimal configuration in this set. So even if the set is not totally ordered, we may have a minimal and a maximal configuration in that set. This is an example. So, well, and now we will connect these sets which are ordered with random chains which keeps the order. What I mean by a random chain keeping the order is the following. I want for each configuration eta run a Markov chain which at time 0 say it's equal to eta, and such that, so I want for each configuration eta in omega define a Markov chain. So I have a Markov chain, a transition matrix P. I want to define, couplings of this Markov chain with the following property. At time 0, I want the Markov chain x eta to start from eta, and I want that if eta is bounded by xi, I want the Markov chain x eta to remain bounded by the Markov chain at time t. So if you start from a configuration eta which is smaller than xi, and this set has not to be totally ordered, I just want it to be ordered, then I want the Markov chain to keep the order. To keep the order in the following sense, that if eta is bounded by xi, then for all t, the value of the Markov chain at time t, for the one starting from eta, will be bounded by the Markov chain at time t for the configuration starting from the configuration xi. So I want to give you an example of a set which is totally ordered, of Markov chain, and define a coupling which keeps the order of this Markov chain. So here is the example. This is a totally ordered set, omega, let's say equal to 1 to m. And now, let me consider a Markov chain, which jumps as follows. So if you are at 1, you can jump to 1 with probability 1/2, and you can jump to 2 with probability 1/2. If you are at m, you can jump to m with probability 1/2, and you can jump to m minus 1 with probability 1/2. And while you are at 1/2, at k, you can jump to k plus 1 with probability 1/2, and to k minus 1 with probability 1/2. So this is a Markov chain, and what I claim is that it's possible to construct a coupling between a Markov chain x1 up to the Markov chain xm, such that xk at time 0 is equal to k, and such that xkt is bounded by xjt for all t larger than 0 if k is larger than j. So this is what I want to show. And in the way we will do it, just we'll use the algorithm I propose in order to construct Markov chain. So let me consider a sequence U1, U2 of IID random variables which are uniformly distributed in the interval 0, 1. And let me define phi. So phi 1 of x will be either equal to 1. So if the value of u is small, so if the value of u of this random variable u, it is between, or let's say t, belongs to the interval 0, 1/2, the Markov chain will try to decrease its value, or if it's not possible to decrease its value, then it will keep it constant. While if ut belongs to 1/2 1, then the Markov chain will try to increase, or if this is not possible, to keep its value. So phi 1x, well, the value is between 0 and 1/2. It's impossible to decrease because the chain takes value only 1 and 0. But so we'll define it 1 if x belongs to 0, 1/2. And it will be equal to 2 if x belongs to 1/2, 1. For kx, now k running from 2 to m minus 1, so this chain can always jump by 1 plus or minus 1, so that will be equal to k minus 1 if x belongs to 0, 1/2, and will be equal to k plus 1 if x belongs to 1/2, 1. And finally, fmx will be equal, well, we can decrease it by 1, so it will be equal to m minus 1 if x belongs to 0, 1/2, and it will be equal to m because we cannot increase it by 1 if x belongs to 1/2, 1. So this defines these functions, phi, and now I will set x k at 0 it's equal to k between 1 and m, and I will use this function and the random variables u in order to define the Markov chain. So x k n plus 1 will be equal to phi x k n un, and this for all n larger than 0. So since I'm starting u from 1, let me take here un plus 1, and this for all n larger than 0. So this defines the chain, and now what I claim is that x k n it's less or equal than x j n for all n larger than 0, provided k it's less or equal than j. And well, mind, because since I'm using here the same value, if I want, I will prove this by induction. I don't want to erase the definition of phi, so let me try to use this part of the blackboard in order to prove that. So I want to proceed by induction. Now, it's true for n equal to 0, because for n equal to 0, xk 0 it's equal to k, xj 0 it's equal to j. Now assume that it holds for 0, 1 up to n, and we want to prove it for n plus 1. So I want to prove that x k n plus 1 it's less or equal than x j n plus 1. But by definition, x k n plus 1, this is equal to phi x k n u n plus 1, and this is equal to phi x j n u n plus 1. Mind that the second coordinate it's equal. So if I prove that phi kx, or phi, let me use different letters now. If I can prove that phi ax it's less or equal than phi bx, if a it's less or equal than b, and this for all x, I'm done. Because by assumption, by the induction assumption, I'm assuming that xkn is less or equal than xjn. So now, if it's true that phi ax is bounded by phi bx for all x when a is less or equal than a, I will get that, well, since this one is bounded by that one by induction, then phi of this one will be bounded by phi, because this holds for all x, and here I have the same u updating the two chains, I'll get that inequality. So the only thing I need to check is that this quantity holds. And this is clear because, well, if I compare k and j, where k and j are between 2 and m minus 1, this is the definition, and if k is smaller than j, then phi kx is smaller than phi jx. So that shows this inequality provided a and b are bound between 2 and m minus 1. And now you can check that if you compare phi kx with phi 1x, since k is larger than 2, that can be at most 1, and this will be 3. So it's clear that phi kx is larger than phi 1x and bounded by phi mx, because k is larger than m minus 2. So here I'll get here m minus 1, and that it's bounded by m, while k minus 1 will be bounded by m minus 1. So maybe I went too fast in order to prove this inequality, but it follows immediately from the definition. So I leave it to you to check that indeed this inequality holds, which means that if a is less or equal than b, then phi ax is less or equal than phi bx for all x. And from this inequality, we can prove by induction that this inequality holds for all n. So we have a set which has an ordered. We have a Markov chain, which is given by a transition matrix. I raised the definition of the transition matrix, but what I proved is that it's possible to define a coupling of these chains in such a way that if I start from two different conditions, one which is below the other, then this relation remains for all n. So this relation remains for all n. And so we will use this possibility, so this property of certain Markov chains, in order to simplify Propp-Wilson algorithm when the set has an order and when the dynamics preserves this order in this sense, when it's possible, so when this algorithm preserves the order. So in order to understand the next lecture, it's very important for you to understand this example. So I ask you really to check by yourself that this relation holds from the definition of phi, and to convince yourself that indeed it's possible. So indeed this construction provides a family of Markov chains which are order preserving in this sense. And so in the next lecture, we will use this idea in order to simplify the Propp-Wilson algorithm and to apply it to a very interesting example, which is the Ising model.